We're going to talk about collisions today. Oh, you'll need a calculator. So we talked about impulse and momentum yesterday. Today I want to talk about collisions. The thing I want to call your attention to from yesterday is that, I'll wait, but come on, get your shit together and stop talking when I'm talking. There we go. Impulse obeys Newton's third law. So when we talked about the idea of impulse yesterday, I tried to indicate towards the end of class that if you are in contact with something, you are applying a force. And because of Newton's third law, the force has to be the same on both objects. And because you cannot touch something without it also touching you, the time of contact has to be the same for both objects, which means that impulse obeys Newton's third law. What you probably didn't take away from that, and it's not easy to see this unless it's kind of put right in your face, is that if we have two objects and they are going to have a collision, we're going to do the carts on the tracks in a minute. Again, we have two objects and they're going to have a collision. The moment the first object becomes in contact with the second, so this is object 1 and this is object 2, I don't think it's a stretch to say that object 2 is going to experience an impulse in that direction. When car 1 hits car 2, because car 1 was moving, and it hits car 2, it's going to push on car 2 to the right. No big deal there? Everybody follow that okay? Well, by Newton's third law, car 2 pushes on car 1 to the left. So there must be an equal and opposite impulse on car 1 from car 2. This is Newton's third law. But impulse is also change in momentum, which means that car 2 experiences a positive impulse, a positive change in momentum, while car 1 must experience an equal but opposite change in momentum. So the car 1 pushes on car 2, increases its momentum. Car 2 pushes on car 1, decreases its momentum. But the amount of the change in momentum is the same. Now, here's the part that you won't catch on to right away, but if you add these two things together, the net change in momentum is 0. In any collision, the net change in momentum is 0. In any collision, the net change in momentum is 0. This means that momentum is conserved. Momentum conservation is one of the most solid conservation rules in nature. Momentum is always conserved in any collision. Momentum is always conserved in any collision. That means that the momentum of the system doesn't change. That means the momentum of the system doesn't change. Individual objects might change their momentum, but the total momentum doesn't change. So for every increase in momentum, something else is suffering a decrease in momentum. So that plays out in all collisions. All collisions in nature obey this principle. So, and what that might look like. I have your 500 gram car traveling at 2 meters per second to the right. There is a 500 gram car at rest. Clearly, there's going to be a collision. Let's say in the course of this collision, the first car is now going 1 meter per second. How fast must the other cart be going? So there was a collision. The collision occurred when the two cars were in contact. And after contact, the first car slowed down. But that meant the second car sped up. This is a pretty standard collision question. In collisions, the momentum of the system stays the same. Now remember, there's three important things here you have to understand. And if you get all these things down, you'll never get one of these wrong. The momentum of the system always has to stay the same in a collision. First thing, we are talking about the moment before contact and the moment after contact. I'm saying that because we're not talking about way in the future where something else might happen, like friction or air resistance or something. I'm saying the instant before the two things touch and the instant after the two things separate, the momentum is equal. That's the first thing you should put in your notes. The second thing you should put in your notes. Remember, momentum is a vector. Remember, momentum is a vector. It has direction. So don't forget to decide what direction is positive. The third thing you don't want to forget, every object potentially has momentum. You add up the momentum before, and you set it equal to the momentum after. This is how collisions work. The momentum doesn't change, so the momentum of the system before the collision will have to be equal to the momentum of the system after the collision. Three things. You got those three things down? So, with those three things in mind, I've established that the right is going to be positive. I'm looking at the instant before and the instant after the collision, and I recognize that object 2 has no momentum before the collision. Object 1 has a mass of 500 and a velocity of positive 2 meters per second before the collision. Remember, momentum is mv, and v is the vector. After the collision, object 1, 500 grams, has velocity 1. So, object 2. It's likely going to be 1. I made the first example pretty easy. But that's it. That's a standard conservation momentum question. You add up the momentums of what happened before and compare them to the momentums of what happens after. This kind of collision is called an inelastic collision. Most collisions in nature are inelastic. You're going to tell me what inelastic means. It's really easy for you to do. I would like you to take a moment and tell me what the kinetic energy was before the collision and the kinetic energy after the collision. You know how to calculate kinetic energy, so I will wait a moment or two, but you calculate the two kinetic energies, the kinetic energy before and the kinetic energy after. I will pick on two people, one to tell me what the kinetic energy was before and one to tell me what the kinetic energy was after. I will wait patiently.
On the whole system or on just one of the cards?
The whole system, on the kinetic energy of the system before the collision and the kinetic energy of the system after the collision. Now I'm hearing a conversation. Yeah, you should probably put the 500 grams in kilograms when you're calculating kinetic energy. You probably should. That would be 0.5 kilograms.
First one?
All right, so we should be about done. That isn't too hard. So, I don't know. Who wants to tell me the kinetic energy before? I could just pick you up. Go ahead.
Is it 1?
How'd you come up with 1?
We'll do 1/2 times 0.5, and then times 2 squared.
Yep, it's 1 joule. It's that simple. Not a really hard problem there. Who wants to do the kinetic energy after? Okay, I should go ahead.
Is it 0.25?
How'd you get that?
Because I plugged in 1 into 1/2 NV squared, and I plugged in 0.5 for N,
Okay.
and then I solved and I got 0.25.
Is that for both cars or just one car?
That is for the first car.
The first car. So we need to do the second car too. But you need to know how fast it's going. I don't think it's hard to realize how fast it's going. Did you guys figure out how fast it's going? It's 1, right? You solve that for V, and you find out it's 1. So it'd be 0.25 again. Yep. So the total kinetic energy after the collision is 1/2 joule. That's what makes it an inelastic collision. Inelastic collisions lose kinetic energy. That's why it's an inelastic collision. Inelastic collisions lose kinetic energy. The energy is transformed into something else. Generally, it makes noise, heat. It can deform the object, cause dents, stuff like that. But generally, an inelastic collision is any collision where you lose kinetic energy. Almost all collisions in nature are inelastic collisions. Now, there are 3 types of collisions. The general form of a collision is this one. This one's inelastic. Our next example is one that's called perfectly inelastic. They will put that word out there, and you'll have to know what the difference is between inelastic and perfectly inelastic. So let's talk about what an inelastic collision is. Let's talk about what a perfectly inelastic collision is. A perfectly inelastic collision still loses kinetic energy. But in a perfectly inelastic collision, the result is that the 2 objects stick together. In a perfectly inelastic collision, the 2 objects stick together. So, I want you to interpret what that must mean and tell me how fast are they going after this collision. Come on, I'm choosing super easy numbers here. This one shouldn't be tough. But if you're having difficulty, we went from having 2 separate objects to having a single object, which means the mass of my object is now, the mass of my object is going to be the total mass of both cars. They are moving together with 1 velocity. In a perfectly inelastic collision, the objects are sticking together. Therefore, after the collision, there's only 1 velocity. And they both must have the same velocity. That's all you have to do. And of course, in this example, how fast is that velocity? Yeah, it's 1 again. Find out the velocity here is 1 meter per second. When objects collide elastically, something different happens. But if it's inelastic, kinetic energy is not conserved. Energy is lost. Perfectly inelastic, they stick together. So if the problem sets up a collision and says they collide perfectly inelastically, then that's telling you they stick together. All right? There is a third classification of collision, which we won't do very often in here, but you need to know what it is in case it comes up. It's mathematically a little more complicated. It is an elastic collision. Elastic collisions are rare in nature. In fact, they really don't happen in nature. We can get close, we can have things that approximate it, but to have a truly elastic collision, we're talking about like subatomic particles and stuff like that. They just don't happen that much in nature. But an elastic collision conserves both momentum and kinetic energy. Okay, so in a elastic collision, both momentum and kinetic energy are conserved. That's mathematically more complicated because it generates two relationships, and one of them, all the velocities are squared. That makes for a pretty complicated question. Generally, you shouldn't expect too many of those. You can be asked to verify if a collision is elastic, but generally you tend to not use elastic collisions in a predictive way. So, I'm going to have you guys practice. We've had a few moments. One of the most common problems on the AP exam is the dart into a block problem. So we'll have one here. I have a 0.5 kilogram dart at 20 meters per second. The dart is going to collide with the block. And I want you to consider three possible ways the dart could collide with the block. First, let's say the block is 10 kilograms. So outcome number one, the dart passes through the block and emerges on the other side. Now there's a hole through the block, but it emerges on the other side, but it's only traveling 4 meters per second. What's the velocity of the block? So I'll give you a chance to try that out. It won't be 16. Try it out. See if you can do this one. Go through the set of steps I gave you. It's really not that hard. Once you've done a couple of these, you'll find that they're pretty easy. We're going to do 3 in the next 10 minutes or less. We're on PEP assembly schedule today.
So what we were exactly looking for is
Velocity of the block.
velocity.
The arrow comes out of the block. What's the velocity of the block?
I think it's 0 because there's no velocity at the beginning. Yeah, okay.
That's first.
All right, so about done. There's really not very much to do here. The momentum before has to equal the momentum after. Choose a direction for positive. I'll pick to the right to be positive. I have 0.5 kilogram arrow traveling at 20 meters per second. The block has no momentum before the collision. After the collision, I don't know what the block's velocity is, but I know the arrow is traveling in the same direction and it still has a mass of 0.5, but now its velocity is 4. This is it. This is all there is on collision questions. They are really straightforward. So, beforehand I had 10 kilograms meters per second, and that must equal 10V plus 2 kilograms meters per second. So it looks to me like V has to equal 0.8 meters per second. The reason it's not 16 is the block was heavy, so the arrow was not particularly effective at moving it. Now, okay so far?
Yeah.
So just, I don't know if you guys have this kind of ability, but if the arrow were to get stuck in the block instead of passing through, do you think the block would be going faster or slower?
Faster.
Yeah, it would be going faster. It would have caused a bigger change in the arrow's momentum, so the block would have to have a bigger change in momentum. So prove that, please. How fast would the system be traveling if the arrow got stuck instead? And remember, nothing has changed about the original circumstance, so the left side is still 10. You don't have to redo anything there. It's just that now the block is stuck, the arrow is stuck in the block.
Three. Oh.
Add two masses together, 10.5.
It's 0.95, right?
What's that?
Together.
0.95 is the
I'm
answer.
stupid.
Yeah.
I don't know what my answer is, but it's going to be less than 1, right? So what'd you get? 0.95?
Yeah.
I'd say that, because we're going to set this equal to 10.5V equals 10, so V 0.95.
Oh, because he added.
Forgot about the arrows.
I had a feeling. That's why I was throwing it out there. So this one would be perfectly inelastic because the arrow got stuck in the block. All right, so one more. What if instead the arrow bounced backwards at 2 meters per second? Will this thing be traveling faster or slower than before?
Faster.
Now think about it. The arrow had to be stopped and turned around and sent back. That's a bigger change in momentum. So the block is going to have also a bigger change in momentum. Now I purposely want to see if you make a screw up here. So I'm not going to help. I'm just going to wait patiently and then walk through and see your work. So try this one and see what you come up with.
It's moving back at 2 meters.
Oh yeah, I said I'd wait patiently. All right, that should be enough time.
How do you differentiate elastic?
I finished my introduction.
Will they tell us?
I was going to get over it.
Will they tell us this was?
All right, so we got a good job out there. Most of you saw that one. A few of you had some missteps. Yeah, it is the arrow that has a negative velocity now. Once you realize that, there's really nothing else I can do, right? If you've discovered that, you understand how this works now. And there's really not a lot to do here, but this one I'll finish out so we get V equals 1.1 meter per second. Collision questions are pretty easy. They're not particularly challenging. We can make them more complicated. There's other things that can be done here to add complication. Both objects could be moving before the collision. We are doing what are right now one-dimensional collisions. The truth is, we should do two-dimensional collisions. They're more frequent. I mean, anybody who plays pool, you know that kind of stuff. Football, all of these things, baseball, they all have two-dimensional collisions in them. It's not really part of our curriculum, but we're going to do a two-dimensional collision lab next week, only because it's a relatively easy lab. It's very visual, so I think you guys will like it. But at the same time, if you can do this, you've really got mastered what there is for collisions, because there's really not much outside of this. Now, before you guys pack up, I want you to understand that this isn't what's going to be on the exam. Tends to use collisions in other ways. Like usually, if a collision is going to turn up in a problem on the exam, they're going to make the collision a portion of another problem and test both subjects at once. This is really common. So in a problem like this, they would say that the blocks stick together after the collision and then ask where they strike the ground. So they make the collision a portion of the problem to see if you understand how to deal with the collision, and then they turn the problem to something else. So obviously projectile motion is this example. And that's how collisions generally are added to the exam. So having an entire question about a collision, really unlikely. Having a question that's got a collision in it, very likely. This tends to be what they like to do. So it can be this, it can be quite literally, a block hanging on a string, an arrow strikes the block, and the block and arrow swing upwards. So they ask questions like, what was the tension in the string right after the collision? That's a force question. Or they ask what the angle is that it makes here. That's an energy question. So the collision is a portion of the problem, but it's not the main event. So those are the kinds of ways in which collisions tend to get worked in to the exam questions. So momentum it feels like it's a small portion, like we're really quite done with all there is for momentum. We're going to do some elastic stuff on Monday just to talk about it and some lab activities with it. But when it comes to calculation, collisions are easy. Momentum before equals momentum after. But because of that, they work them into the problems like this. All right, that's all for today.